Matrices are everywhere, as if they have a kind of fear of missing out. These are just 4 examples though. In quantum mechanics, we use Pauli matrices to account for weird mechanism of spins, which is an intrinsic angular momentum and a purely quantum phenomenon. In business, and in the context of stock markets, we can use matrices to anticipate how the market might be in 20 weeks. Engineers use matrices a lot. For example, in electrical engineering, we can find electrical currents in different parts of a circuit using some linear equations that can be presented by matrices. And also in data science, and more specifically in image processing, an image can be seen as a matrix. Each pixel is associated with a number showing how bright or dark the pixel is, or even we can use some other numbers as elements that represent the color codes. So the question you might ask here is, what is a matrix? Let's investigate this question using a social example. Suppose we have a group of people, some of them are friends with each other. For example, as the name suggests, FOMO is friends with all of them, and we use these lines to show they are friends. Alice is friends with Bob and Charlie, and Emma is a friend of Diana. Whenever 2 people are friends, we use number 1, showing that there is a mutual connection between them. For example, Alice and Bob are friends, so we use 1 to show their friendship. Whenever there is no connection between the 2 people, we use 0 to quantify these relationships. For example, there is no line between Bob and Diana, so they share a 0. Let's try to sort these numbers in an array you know is a matrix. Let's label each column by the first letters of these people, and also the rows by the same letters. As you can see, this is a 6 by 6 matrix. The first number represents the number of rows, and the second number shows the number of columns. We know that Alice is friends with Bob, Charlie, and of course FOMO, so these elements are 1. And the other elements related to Alice are 0. Alice is not friends with herself, which is psychologically bad for her, and also with Diana and Emma. And in the same fashion, we can fill out the rest of the matrix or this array of numbers that show the relationships between a group of people. Now, let me ask you the question one more time. What is a matrix? You might be thinking of the graph we were just talking about. Now, what if I add these 2 column matrices? Yes, these are also matrices, column matrices that are also called vectors. This matrix is now a representation of 6 linear equations that are sorted out using a matrix and 2 column matrices. I bet you are still thinking about FOMO. So let's get back to our friends. If we multiply these 2 matrices, we'll get this new matrix. I'm going to show you later in the video what matrix multiplication is and how we can do it. These numbers show how many mutual friends each person has with themselves. In other words, how many friends they have. Take a look at these 2. They show that Alice and FOMO have 2 mutual friends. This is also true for Bob and Charlie. The other ones you see in the matrix show that all of them have at least 1 mutual friend, and that mutual friend is FOMO. At this point, you might wonder why the multiplication is an array of numbers showing the number of mutual friends. Let's call these 2 matrices M, and the multiplication of the same matrix with itself M squared. Each element of M squared matrix can be represented by 2 indices I and j. We can calculate each element of the new matrix by multiplying corresponding elements of the first row of the matrix on the left with the element of the column of the matrix on the right and add the 6 outcomes. In fact, by this summation, we are eliminating the first connection and paying attention to the second order connection between the people. For example, for this specific element, we use the second row and the third column. In fact, we are checking whether Bob and Charlie have any mutual connections with the other members of this society or not. Now, one more time, what is a matrix? Try to think about anything else other than this. Regardless of what a matrix represents, we are going to see what properties a matrix has and what operations we can perform on it. This is a matrix which has m rows and n columns, and the elements are shown by the letter A and 2 indices. The first index shows the row, and the second the column in which the element is located. Let's call this matrix A. It is very important to define the set over which a matrix is defined. For the purpose of this video, we are going to choose real numbers. For example, in quantum mechanics, we use complex numbers as you saw in the beginning of the video for Pauli matrices, and you saw in the graph example that for the matrix we used natural numbers. In more advanced concepts in physics, we can use vectors as the elements of a matrix. Now that we know what set the elements are defined over, we can say that this matrix is defined on this set, which is the set of all real valued m by n matrices. In the same way, we can have an array of real numbers stacked upon each other. There are m rows and just one column. We call it a column matrix. And also we can sort the elements in a row, having just one row and n columns. This one is called a row vector. One of the operations we can do by matrices is addition. Suppose that we have two matrices A and B, and both of them live in this space. The element on the ith row and jth column is the simple addition of the corresponding elements of the matrix. For example, to add these two matrices, we just need to add the two corresponding elements, and it yields the new matrix for which each element is the sum of the corresponding elements of the matrices A and B. Pay attention that we cannot add these two matrices, because the first one is a 2 by 2 matrix, but the second one has a different dimension and is a 2 by 3 matrix. We also have matrix subtraction, which is just like matrix addition, but the elements of the second matrix are all multiplied by a -1. The next operation is matrix multiplication, which you have seen earlier in this video. Suppose that, again, we have two matrices with the same dimension. Can we multiply these matrices element-wise? There is such a product called element-wise multiplication or Hadamard's product, but it is not the definition of matrix multiplication. We can multiply two matrices if the number of columns of the matrix on the left is equal to the number of rows of the matrix on the right. In this case, the elements of the new matrix are the sum of the multiplication of corresponding elements on the ith row of the first matrix with the elements of the jth column of the second matrix. Take these two matrices for example. The first one is a 2 by 3 matrix and the second one is a 3 by 2 matrix. These two numbers show the dimension of the multiplication. So the outcome will be a 2 by 2 matrix. The first element of our 2 by 2 matrix can be calculated using the first row of A and the first column of B. We multiply the corresponding elements and the answer is 2 plus 0 plus 9, which yields 11. For the next element, we get 9. The next element is associated with the second row of A and the first row of B, which yields -3. And finally, the last element is -1, and this 2 by 2 matrix is the matrix multiplication of A and B. Now, what if we want to calculate the multiplication of B with A? Is it possible? B is a 3 by 2 matrix and A is a 2 by 3 matrix, so it is possible, and the result will be a 3 by 3 matrix. Again, we have to take each row of matrix B and multiply the elements by each column of A and add them to find the elements of our 3 by 3 matrix. This example shows that matrix multiplication is not commutative, meaning that the order of multiplication is very important. So far, we have investigated matrix addition, subtraction, and also matrix multiplication. But can we define matrix division? For real numbers, we can write the division as the multiplication of one element with the inverse of the other element that is in the denominator. And also, when a number except 0 is divided by itself, it gives 1. We can also say that when a number is multiplied by its inverse, it yields 1, which is the identity element under multiplication. We also have an identity element under addition, which is 0. Now that we are talking about matrices, you might want to know what the identity element for matrices is. We define an identity matrix to be an n by n square matrix. All the elements are 0 except the ones on the diagonal, which are all 1s. So there are n elements on the diagonal which are 1 and n squared minus n0 elements. Take this matrix as an example. The elements are real numbers and the dimension is 2 by 3. We can multiply this matrix from the right with a 3 by 3 identity matrix. And the result would be the same matrix. If we do the same thing with a 2 by 2 matrix, but this time multiply from the left, again we get the same result. Obviously, if we multiply the matrix from the left and right by these two matrices, we will get the same matrix. So, for every m by n matrix, we can multiply the matrix from the right and left with the identity matrix, but we need to pay attention to the dimension of the identity matrix we are using. Before investigating whether we have division or not, let's take a look at some other properties of matrices. For every 3 matrices with these dimensions, it doesn't matter whether we first multiply A and B and then multiply the result with C, or first multiply B and C and then do the multiplication with A. It is really important to pay attention to the dimension of the matrices when we are multiplying them. This property shows that matrix multiplication is associative. Now, take these 4 matrices. A and B have the same dimension, and C and D also have the same dimension, but different from A and B. Pay attention that the number of columns in A and B is equal to the number of rows in C and D, so we can multiply both A and B with C and D from the left. We can also add A and B and then multiply with C, or similarly multiply them with C and then add them. We can also write the same thing for the addition of C and D. Again, with matrix multiplication, we have to pay attention to the dimensions. This property shows that matrix multiplication is distributive over addition. Okay, let's get back to division. In fact, matrix division is not defined in linear algebra, but we can do something that looks like division operation. For square matrices, we can define a matrix that when multiplied by the matrix itself, gives the identity matrix. We are still using the multiplication operation, but multiplication with the inverse of a matrix yields identity matrix. This matrix is called the inverse of the matrix. One of the ways of finding the inverse of a matrix is Gauss-Jordan Method, in which we use elementary row operations to find the inverse of a matrix. The idea is to use an augmented version of our matrix by adding the elements of an identity matrix on the right, so our matrix becomes an n by 2n matrix. The idea is to manipulate the n rows of the augmented matrix to change the left side of the matrix to an identity matrix, and amazingly the inverse of the matrix appears on the right. There are 3 allowed row operations. The first allowed action is that we can swap 2 rows but not columns. The second thing we can do is multiply a row by any non-zero scalar, and finally we can add or subtract the multiple of one row to another. Let's see an example so you can see how it is done. We want to find the inverse of this 3 by 3 matrix using Gauss-Jordan method, also known as Gauss elimination method. The first step is simply creating the augmented matrix. On the left side, we write our matrix, and the identity matrix elements go on the right side. In the first step, we subtract twice the first row from the third row. The first 2 rows remain intact. And by changing the third row, the first element on the left goes to 0. This is the next element we want to eliminate. Again, we change the third row by adding the second row to it. We really get lucky here because the element on the third column becomes 1. Otherwise, we would have had to divide the second row by a number to get 1. This is our next target. We have to manipulate the second row. This time, the first and the third rows remain the same, and we subtract twice the third row from the second row. Pay attention that now the third row have become a weapon to eliminate only the elements on the third column. Now, we have another weapon that only kills the elements on the second column. So let's use it and eliminate this element on the first row. This time we manipulate the first row by taking twice the second row out of it, and as a result, the second element on the first row goes to 0 and the second and third rows remain the same. The last step is eliminating this element. We use the third row to eliminate this number 4, and you can see that on the left, we just have an identity matrix, so the square matrix on the right is the inverse we were looking for. If we multiply these two matrices, the result is the identity matrix. Another important operation we can do with matrices is the transpose of a matrix. If we have an n by n matrix, the transpose of the matrix is an m by n matrix and is shown by a sign t as a superscript. To find the transpose of a matrix, what we need to do is change the rows and columns of the matrix. The columns of the transpose are the same as the rows of our original matrix, and its rows are the same as the columns of our matrix. For example, if this is our matrix, the transpose can be derived by changing the rows and columns. So the first matrix is a 2 by 3 matrix and the second one is a 3 by 2 one. If we multiply A and A transpose, we will get a 2 by 2 matrix. But if we use the transpose on the left, we get a 3 by 3 matrix. These elements in these two square matrices are on the main diagonal. If we want to change the rows and columns of these matrices, or in other words, if we find the transpose of these two matrices, we would get the same matrix. These kinds of matrices are called symmetric matrices. The transpose is the same as the original matrix. More interestingly, you saw that the product of a matrix with its transpose is a symmetric matrix. Pay attention that symmetric matrices are square matrices. This is a very important property for the transpose of the product of two matrices. If A is an n by m matrix and B is an n by p matrix, B transpose would be an p by n and A transpose would be an m by n matrix. In this case, we can multiply the two matrices. We already know that the ith and jth elements of the multiplication of A and B can be expressed in this way. If we take the transpose, each element changes the order of rows and columns, and we'll have this expression for the left side of the expression above. As for the right side of this expression, we are multiplying the transpose of B with the transpose of A that can be written element-wise in this form. But we know that by changing the orders of the elements, we can get rid of the transpose for both matrices. And finally, we are left with the same expression as we found for the left side. Now, by using this important property of transpose, we can prove that for every matrix, the multiplication of the matrix with its transpose gives a symmetric matrix, as you can see by these two expressions. We also have a similar property for the inverse of a matrix. If we have two square matrices with the same dimension that are multiplied by each other, we expect this expression to be the identity matrix of the same dimension. Let's multiply both sides from the left by A minus 1. We get an identity matrix here. Now multiply B minus 1 means the inverse of B from the left. This is another identity matrix and the expression above is derived. In the next video, we are going to use matrices to solve systems of linear equations.